I think we're going to have some fun together. Come with me. Well, I hope those devices captured your interest. We'll get back to each of them in more detail as their operation relates to the particular topic that we're exploring throughout the series. So for over the last 140 years, electricity has gone from a curiosity for scientists to part of our almost every aspect of our everyday lives. And that's going to continue as we combat climate change. Electricity as a conduit for moving energy from where we have it to where we need it is going to expand. It's going to help us bring renewable energies from one region to another and sometimes take it in the other direction depending on the time of day, the time of year, and weather conditions. It'll also help us transform our ground transportation system from relying heavily on fossil fuels to clean energy resources. I want to provide you with a visual experience of a phenomena that is often hidden or seems almost magical. Now, before we start our structured sequence of going from fundamentals to more complex concepts to devices that we use in our everyday lives that rely on electricity and magnetism, I'd like to share with you a couple of devices that will demonstrate a force that's extremely important for our electrical world and also life on Earth. We'll be coming back to this force over and over again. So I'm going to start with this block of wood, and this block of wood has a slot in it, and this thin piece of wood fits in there very loosely, no friction. And I'm going to drop this thin piece of wood through the slot, and we'll see what happens. Well, it just seems to fall and accelerate just like it would if there was no block of wood. We're going to do the same thing, but we're going to use this piece of aluminum. Now, aluminum is a very good conductor of electricity. So I'm going to drop that through the slot, and let's see how it behaves. It almost seems like it's floating through. It's not being accelerated as quickly as it goes through the slot. Out here it would fall very quickly, but through the slot it seems to be going very slowly. Now you're probably guessing this is not any ordinary block of wood, and you'd be right. Yes, it has magnets on either side of the slot. But aluminum is not magnetic. So let's take a look at a diagram to see what's going on. So here's the block of wood, and this part of it is where the slot is. And the aluminum is shown in this gray color right here. And as it moves through an intense magnetic field shown in blue, the little blue circle represents that very intense magnetic field. As the aluminum moves through that intense magnetic field, it produces electrical currents shown in red. As electrical currents start to flow, they interact with the magnetic field and they produce a force in the opposite direction of motion. So if the aluminum is moving downward, it experiences a force upward. If we were to pull up on the aluminum through the magnetic field, we would experience a retarding force in the opposite direction. Now here's a device that's shaped completely differently, but it's going to demonstrate the same effect. I have a permanent magnet here, and over here I have a little pendulum that's made with a stick and a sheet of copper. Now I'm going to give you a different view of the magnet so that you can see a little better how it's put together. So here's the South Pole, the North Pole, and these two bolts create a very intense magnetic field in that air gap. I'll show you that here with these two pieces of steel. You notice that a very strong field right there. There we go. However, copper, like aluminum, a very good conductor, is not magnetic. No effect at all. Now this little pendulum here, would probably go back and forth like that for a whole minute until the friction of the pivot and the air resistance used up its energy. We're going to swing that through that magnetic field and see what happens. You ready? Here we go. It won't pendulum. Whoops, I hit the bolt that time. So, well, we'll just use that technique. You notice it's not over here, it would just swing fine, but through the through the magnetic field, it is not penduluming. You get my point. So let's take a look at why that's happening. So let's take a look at why the pendulum slows down and won't pass through the magnetic field readily. So here's the stick, and at the bottom is that sheet of copper, and that little blue circle represents the poles of the magnet. The magnetic field is really strong. Now, as we bring the pendulum back here and let it swing through, as the copper goes through that magnetic field, it generates electrical currents, shown here in that kind of a dark brown, reddish brown color. And again, as the electricity starts to flow, as the electrical currents start to flow, they interact with the magnetic field. And so they produce a force, again, in the opposite direction of motion. So if the pendulum's moving that way, it experiences a retarding force in that direction. If the pendulum's moving that way, it experiences a retarding force in that direction. And that's why it slows down. Our third device, which demonstrates the same force, is this series of concentric tubes here. I've got a copper tube, an aluminum tube, and a copper tube. They could all be copper, they could all be aluminum, they could be any combination. We would get the same result. Okay, it doesn't matter. It was just, those were the ones that were conveniently available. Now, I'm going to drop 3 devices down the tube, and you're going to tell it that it went all the way down because it's going to make a noise when it hits the bottom. I'm going to drop a piece of brass. These are all loose fitting. They don't rub against the side of the tubing. They're all skinnier than the tubing. So here's a piece of brass. That was less than a second, wasn't it? And here's a little piece of wood. And here's a piece of plastic. So they all fell down there in less than a second. Now I'm going to drop a magnet. There's a magnet in my hand here on the end of this nail. Let's go to the camera from up above so you can see. Here's the magnet. I'll pull it off for you. And there it is. And we know that copper and aluminum are not magnetic. Okay? They're not magnetic. So I'm going to drop the magnet down the tube. It looks like we're lined up pretty well, and let's light up the bottom here. There we go. Okay. It's a little better there. Whoops. Okay. So what I want you to do is I want you to help me. I want you to count. We're going to time this, okay? Remember, the other particles, the other objects fell in less than a second. So we're going to time how long it takes the magnet to go. And we'll time it with without a watch. We'll just say 1001, 1002, 1003. So you start counting with me as soon as I say go. I'll say get ready, get set, go. So here we go. Here's the magnet. Get ready, get set, go. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010, 1011, 1012, 1013, 1014, 1015, 1016. That took 16 seconds, more or less. Wow, a lot longer. Let's take a look at why that took so long to fall. So this diagram will explain why the magnet doesn't just drop to the bottom of the tubes. Here's the magnet shown in gray. The tube is shown in this orange color. And associated with the magnet, of course, is the magnetic field, indicated in blue. I'm just showing a very limited amount of the magnetic field that goes out here too, but the important thing is to see that it cuts through the tubing, through the conducting tubing, the copper or the aluminum. And as the magnet starts to descend and that magnetic field moves down the tubing. Now that magnetic field is all the way around. It's not just in these two directions. It's all the way around the tubing. As the magnetic field cuts through the copper, it produces electrical currents up here in this direction and down here in the opposite direction. And once that electrical current starts to flow, it interacts with the magnetic field, which is attached to the magnet, and produces a force in the opposite direction of motion. So if the magnet is moving downward, it experiences a force upward. Now I'm going to repeat the experiment with a tube, except we're just going to use the outer tube. The more tubes I had together, the more conduction there was and the slower the magnet went. But this is not as direct a coupling, so it will be quicker, but I thought it'd be fun for you to see the magnet kind of float down, flopping around as it went down. So we're going to do the top view again. There you have the top view. I'm going to drop the magnet. You don't have to count unless you want to. We'll light up the bottom, and I'm going to say get ready, get set, and go. It just took about 3 or 4 seconds to do that. Okay, so what do these devices have to do with our electrical world? Well, I have one more thing to show you. Over here on my left. So I've got this crank I'm turning, and through 2 gearboxes it drives this generator. Now the same force that produced the electricity, when I flip this switch on, the same force that produced the electricity in the aluminum sheet as it went through the slot in the block, and the same force that generated the eddy currents in the pendulum bob, the copper sheet, and the same force that produced the electrical currents in the tube are producing the electricity to light these bulbs. Also, that same force is making it hard for me to turn the crank. Remember how it slowed all those activities down when we generated the electricity? Yeah, I'm getting tired of this. I hope you'll join me in the rest of the series. I'll see you in the next episode, but in the meantime, I could use a hand. See you then.